All right, it's 11:15. I think we'll get started. So sorry I had to move office hours to today, but if you have questions on your homework, I'll be on office hours from 1 to 2, or you can make a Zoom appointment with me. You know, some people can't make any of the office hours and they just say, you know, can we Zoom now? You know, that's not a big deal. So just let me know. I'm happy to customize, especially near the end of the semester. I want to make sure that you get the attention that you need to be successful. And so make sure you turn in your homework. I'm happy to answer questions by email, not too late tonight, but you know, the usual. And I have some grading to do this weekend and update the clickers, but you will know before you take the fourth exam exactly where you stand in the class. So don't blow off the fourth exam if you're doing well and say, well, I'm going to drop this one anyway, because material from the fourth exam, of course, will be on the final. And so you want to make sure that you do the appropriate amount of studying. For those of you that have, you know, one exam that wasn't what you wanted, you know, the fourth exam is a good way to make that up. And so we have extended office hours. We'll review on Monday. So bring your questions, whatever you want to ask. Then we'll take the exam on Wednesday and we'll keep going with just a few more lectures. And so I just want to make sure that I'm available to you as needed. And also I will get your grades fully updated, clickers, everything. So you know exactly what's going to happen going into the fourth exam and the final. Any questions or comments? Anything people want to chat about? All right, we'll try and make this painless today. There's a few of you missing and the weather's nice, so that's just how it goes. But anyway, this is a really interesting lecture because we have to start to think like polymer chains, or we have to think about what the chains are doing that lead to this sort of macroscopic behavior. And so viscoelasticity is a real hallmark of how polymer materials behave. And so if we really pay attention to this idea of chain relaxation, and we really think about, okay, we're going to stretch out chains. Those chains are going to want to coil back up. What is the ramification of that? That really leads us to get some of these properties that are just hard to intuit without thinking about what the chains are doing. So creep, there's a scientific definition of creep, and it's basically increased deformation as a function of time. Time-dependent properties are a hallmark of viscoelasticity. So delta L increases under static load. And the way that creep tests are done is that you put a weight on a material and watch that weight go down, down, down as a function of time. Now what's happening is those polymer molecules, when you put the 5-pound weight on, you stretch those polymers a little bit because you get a delta L, right? So anytime you have a material sitting there, like our tensile bar, you put a weight on it, you stretch those polymers a little bit and you get an initial deformation. And so if we have an initial sample, so here's our initial sample with no load. Right when you put the 5-pound weight on that sample, you get the elastic deformation under initial load. So that's the Young's modulus region, or that's the first part of the stress strain curve where you load up a sample and it elongates a little bit. When you do that, you stretch the chains out a little bit. Now, chains want to be coiled up. We've already established that the equilibrium conformation of these polymer chains is some sort of random coil like we studied in the conformation part. And so in order for those chains to coil back up, they need to relax or they need to untangle. And so creep occurs because chains untangle or relax as a function of time. And as they entangle, the material becomes softer and softer, or the delta L increases if you start to disentangle these chains. So that's the origin of creep, and we want to remember that in terms of chain relaxation. So if we apply our elastic response that we just talked about in the Young's modulus region, where we have that linear stress-strain relationship, then we have a viscous response where if you take a fluid like honey and you shear it, it's permanently deformed. Honey doesn't snap back like silly putty does. If you put that all together, you get this creep viscoelastic response. And sort of sussing out this type of diagram is important because it shows you exactly what's happening to the material, what's elastic, what's creep, what's recovery, and this idea of permanent deformation. So this is a complicated diagram. It's worth looking at this and trying to figure out, okay, we have an initial sample, we put on the load, and this is versus time. This is not stress strain. So initially you put on the load, you get an elastic response. Then from that strain, you get creep, or the delta L goes up, 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 up. So the strain increases as a function of time. That's exactly what we've shown in this diagram right here. So strain increases because we're at constant stress or constant load. And then when you take the weight off, you get some part of this elastic response back. So don't forget that in a spring, you can go both ways in terms of increase the load and you increase the elongation, or you decrease the load and you decrease the elongation. So there is always some part of an elastic response versus something where you stretch it and it permanently deforms. That's the plastic response of the material. And then you have some sort of creep recovery, and then you have permanent deformation as a result of that. So this is worth thinking about what's going on in a creep experiment. Questions on this? Okay, remember there's a scientific definition of creep. All right, stress relaxation. This kind of looks like exactly the same situation, right? But you have to look really closely at this diagram. What this shows is that at constant strain, because the stress is relaxing, so you hold the strain constant. So I'm going to elongate this like a delta L of 20% or something like that. And if I hold that polymer sample at a given elongation, you see the load it can support goes down as a function of time. So in effect, if I'm at a constant deformation and the load or the stress is going down as a function of time, what's happening is my effective modulus is going down, 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 right? Because modulus is calculated from the slope of the stress strain curve. So let's say I'm going to strain it 0.2 or 20%. So this is, say, the 4-pound point. Then I'm at the exact same elongation, 3-pound point, 2-pound point, 1-pound point. So as a function of time, my stress is going down, down, down. And so the effective modulus, the slope of this line, is going down. And it turns out that's also due to chain relaxation. And so when I stretch a polymer, all those chains are stretched out a little bit, or a polymer sample, all those chains are stretched out. And as they disentangle and relax, the material gets softer and softer because of chain relaxation. Due to chain relaxation. So it's the exact same chain relaxation phenomenon that's happening that causes both of these responses. And that's why it's important to know when creep is happening or when you're under a creep situation, constant load, versus when you're under a stress relaxation situation, constant strain, and the load is going down. Yes?
So the more elongated your chains are, the less stiff they are?
So that is a very good question. So let's talk about that. So relaxation has to do with chain motion, right? I'm a chain relaxing, I'm disentangling, I'm moving around other chains. Do stiff chains relax faster or slower than flexible chains? Slower. So that's why we have to think like chains, right? Anything that stiffens the chain, cross-linking, higher TG, crystallinity, physical cross-linking, those things slow down chain relaxation. So it's going to slow down stress relaxation and slow down creep. So it's not that the chains are changing stiffness when we change the sample. You're changing the chain conformation. It's the same polymer. So it's polystyrene to start with. You stretch it out, it's still polystyrene. So you have to think about the intrinsic properties of what those molecules are doing. So for instance, you know that, let's say, well, let's just go right back to here. So polystyrene has a Young's modulus and stress strain curve of 3,100 megapascal. And polymethyl methacrylate has a Young's modulus of 4,650 megapascal. Which polymer relaxes faster, polystyrene or PMMA? Polystyrene. It's softer, or it has a lower modulus, so it's more flexible, and so it will relax faster. So it will creep more, and it'll have more stress relaxation. Does that make sense?
Yes.
Yeah. And so we're going to talk about cross-linking. You know, crystallinity is a hard one because it has both amorphous and crystalline parts, but we'll talk a little bit about that. So we think like chains for these types of properties because it's the intrinsic chain motion, the flexibility, the disentanglement that causes this type of viscoelastic response. And people measure stress relaxation and creep all the time in polymers. Any more questions? All right. So in addition to the intrinsic properties of the polymer chains, temperature plays a big role in this, right? You raise the temperature, and do chains relax faster or slower when you increase the temperature? They relax faster, right? That's natural. You heat the chains up, they move around more. And so creep happens faster at higher temperature, and stress relaxation happens faster. And usually what you see in terms of stress relaxation is this time, and this is plotted as log effective modulus, and this is called the relaxation modulus or the time dependent modulus. And you can see for this polymer sample right here, and it doesn't even say, here's PMMA right here. So it's polymethyl methacrylate, 40 degrees. So this is the zoomed in part, or this is a linear scale, but it's plotted as the log of the number. But this up here, this is probably going to be, you know, compared to this, not too much of a change in terms of how much stress relaxation over hundreds of hours you get for PMMA. So the modulus changes a little bit, or the stress relaxation happens a little bit at 40 degrees Celsius. Of course, as you heat up the polymer, the modulus at time zero goes down, or effectively time zero. We can't plot zero on this log scale, but you know, you heat up a piece of PMMA and the modulus is lower at 110 degrees than it is at 40 degrees. But the slope of the line really start to matter. And so that tells you the slope of the line is the rate of stress relaxation. And that happens much faster at higher temperature because the chains are relaxing faster. So you see a lot of cool plots like this, and eventually you get to pretty low modulus, which tells you that, okay, you know, PMMA is not going to be very effective at this temperature because the modulus is really headed in the wrong direction if we want a stiff material. Whereas, okay, let's think about these temperatures, and we can pick what's called an upper use temperature or an upper application temperature where, okay, the properties of PMMA are pretty good and we shouldn't go above this temperature or else it's just going to relax too fast or it's going to creep too fast. But you definitely want to look at this idea of the modulus changing as a function of time, and that's due to stress relaxation, just as we demonstrated here. Any questions on that? Any comments? Yes.
Why is there a flat part once we get down to like 125?
We're going to talk about that. Yeah. So any flat part in modulus, so the y-axis here is some sort of modulus. Any flat part means it's a constant modulus over a certain amount of time in this case, and that's usually an indication of a rubbery region. You know, the rubber's not changing its stiffness very much over a certain amount of time, and eventually it will flow. But we'll look at a couple plateaus in a second. All right, and of course, if we didn't have any stress relaxation, we'd also have something that's perfectly flat, right? Which means modulus doesn't change as a function of time. All right, you can get out your clickers. Let's see who's here today. Hopefully we'll make 40 people, but I'm not super confident of that. I get it, holiday weekend. All right, so conceptually, do you expect lower molecular weight polymers to relax faster or slower than high molecular weight polymers, all else being equal? Remember, we talked about cross-linking, we talked about TG, chain stiffness. This is another factor in terms of how we expect the chains to move in regards to one another or relax. So do low molecular weight compounds relax faster or slower than high molecular weight? All right, we got 45, 44, that's good. So I think everyone voted for low molecular weight relaxes faster. They have less entanglements. More chain ends. If we're below the plateau molecular weight, they can have lower TG, although let's just assume we're above the plateau molecular weight, but less entanglements will lead to faster relaxation. So y'all got that, that's good. All right. So when we measure stress relaxation, oftentimes this is done using rheometry, or a single stress relaxation plot sort of looks like this. So we have log as a function of time as well. We'll look at log versus log modulus versus temperature as well, but this is sort of just a less complicated example than all of this stuff. So now we're going to define, instead of glass transition temperature, you know, we don't have any temperature on this plot, right? So this is constant temperature. Because one axis is the dynamic modulus, the other is time. This looks a lot like our modulus versus temperature plot that we've seen before. We'll talk about why that is, but make sure you pay attention to the axes. This is at constant temperature. So it's basically one line from this curve. So we have the at short time, we have the glassy region. So if you take a ball of silly putty and you smash it with a hammer, is that a short time experiment or is that a long time experiment? Short time experiment. And what does that silly putty do when you smash it with a hammer? It actually shatters. So if you hit the silly putty hard enough, you can get it to shatter like glass. And so silly putty, even though we experience it as a rubbery, liquidy material, at very short time, it's glassy. Why are polymers glassy at really short times? What about the chains makes the polymer glassy at short times? Yes.
There's no time to.
The chains have no time to move, so they act like a glass. Chains have no time to move. It's not exactly like, you know, when you are at the beach or the lake and you sort of jump into the water, you're like, oh, the water's soft. It feels a lot softer to you than the sand does if you cannonballed on the sand. But when you're water skiing and you fall, the water feels a little harder to you than it does if you just jump in at the shore. That is not viscoelasticity, because water is not viscoelastic. It's due to surface tension and inertia and other things like that. But you could sort of get the idea. The molecular phenomenon is that the chains can't move. It takes time for them to relax. And so if you don't give them that time and your experiment is faster than the relaxation time, it looks glassy. All right. Glass transition region. We know that as you go from a glass to a rubber, the material gets softer, right? And if you give the chains time to move, then the material starts to feel softer. You get into this rubbery plateau where once the material is rubbery, you know, it takes a long time to get those last entanglements out before you get to some sort of liquid-like behavior. When the modulus is going down, down, down like that, that's liquid. And that just takes a long time for that to happen because, of course, liquids don't have any entanglements. It takes a long time for those chains to relax enough to behave like a liquid. And of course, high molecular weight chains take a longer time to relax than lower molecular weight chains, which is what this plot shows right here. What other things other than high molecular weight in red and low molecular weight in blue, what other examples could we come up with of things that relax faster or slower? What about cross-linking? So if we had a cross-linked elastomer versus an uncross-linked elastomer, would the cross-link be red or blue on this curve, if you can see red and blue? Cross-linked would be red, right? Because cross-linking slows down disentanglement, holds chains together. In fact, if you cross-link it enough, you can have a far extended rubbery plateau because you can never get the material to flow, right? What about TG? TG is a proxy for what property of the chains? Stiffness, right? So we could talk about chain stiffness, but more commonly, we say this polymer has a higher TG than this polymer. So which polymer is the higher glass transition temperature, the red or the blue? Red. Higher TG polymers relax more slowly. Remember, glass transition temperature is a thermal property of the polymer. Here, we're addressing the time-dependent property. So even though we call it the glass transition region, you know, it's time that we're really changing in our independent variable in the experiment. So this might be a high TG polymer, and this would be a low TG. And you know, when we talk about high TG versus low TG, we're really talking mostly about chain stiffness and some intermolecular interactions. All right. So for high molar mass polymers, entanglements can cause this plateau. So which curve represents the behavior of, get my clicker going here. Which curve represents the behavior of a linear polymer, A or B? Well, we had a couple more people than that last time. All right. So we just said that something like A would be a cross-linked polymer, and anything that's cross-linked is a network. It's not linear. And so B, I guess it's on the next slide. B is the right answer. Eventually, a linear polymer like B will flow. And so this is liquid like flow. So this A is either a really high TG polymer that hasn't got, we need to go to much higher temperature to get that, or it's cross-linked or something else. Now you notice that now this is, oh, let me stop this. This is versus temperature, log versus temperature. This plot is versus time, modulus versus time. They look exactly the same. What does that tell us about the relationship of time and temperature in regards to polymer viscoelasticity?
Time is proportional.
We can, so that's mostly correct. We can either wait longer and allow the chains to relax, that's time, or we can heat up the chains and they relax faster, that's temperature. And we call this time temperature superposition. So this plot, because temperature is on the x-axis, time is constant. So whatever we're doing to measure the modulus, like a rheometry experiment or a tensile experiment, that's taking the same amount of time every time. Say 1 second, or a frequency of 1, something like that, depending on if we want to express the experiment in frequency or seconds. That's held constant, and we change the temperature. If you take that ball of silly putty and put it in the oven, heat it up, and somehow keep it round, and then smash it with a hammer at high temperature, it won't shatter, or it won't shatter as much as it did at room temperature, because you're allowing those chains to relax faster at higher temperature, even though the time is the same. And so that's really interesting. Instead of waiting, 100 seconds, or sometimes you see plots on the time where it's like 10 to the 5 seconds, that's getting to be a long experiment. You can just heat up the temperature and you can get exactly the same information. And there will be a lot to say in your advanced polymer classes about time temperature superposition. And either Professor Hickey or Professor Colby will ask you, have you guys ever heard of time temperature superposition? And you could say, yeah, we heard about it in 202, but let's go into the details of how to relate one to the other, because there's some quantitative relationships that you can use in order to construct these time temperature superposition plots. And so again, having some feeling for what the molecules are doing, this is all about chain relaxation, and I can either wait for those chains to relax, increase the time, the material will get softer, or I can heat up the material, chains relax faster. If chains are relaxing faster at higher temperature, the material will be softer as well. And so make sure that you are able to equate what the chains are doing with changes in time or changes in temperature. And that's, I think, a new concept for lots of you, but this is fundamental to how polymers behave. It's like when I said every polymer has a glass transition temperature, nearly every single polymer does this without exception. All right, questions or comments? Yes.
So for linear polymers, don't they usually have higher TG?
No.
No.
Linear polymers don't have anything to do with TG. You can have a linear polymer with a high TG. You can have a linear polymer with a low TG. You can have a cross-linked network polymer with a high TG. You can have a cross-linked or network polymer with a low TG. It's really the polymer structure or the monomers that tell you about the chain stiffness, that tell you about the TG. So you need to know what that repeat unit looks like.
So I just remember that we said that branch polymers inhibit crystallization.
Yeah, so crystallization and TG, remember, are completely separate issues. Yeah. We're not talking TM here. We don't have anything with melting on here. Although we could have, here's TG. Where's TM in relation to TG on this plot? Higher temperature, right? And so this could be, depending on what the polymer is, this could be TM where we finally get flow, and A could be cross-linked, something like that. Yeah, we don't quite know where TM is. Yeah, so don't confuse chain stiffness with other things like crystallinity or cross-linking or things like that. Yes?
So crystals don't necessarily mean that it's a stiff material.
Well, it depends on the percent crystallinity. So some rubbers, which are flexible elastomeric materials, have a little bit of crystallinity. Most rigid plastics that are semi-crystalline will be rigid, polyethylene, polypropylene. But you can make atactic polypropylene that has no crystallinity, that's rubbery. Yeah. And then you can cross-link it or something and make a rubber band out of it like A. So crystallinity does confuse things. And I'll try and give you very clear scenarios in terms of what's happening with crystallinity. But you can think about crystallinity acting as physical crosslinks or effective crosslinks that hold the material together and don't allow things to relax as fast. Okay, any other questions? All right, last topic. So we're going to talk a little bit about viscosity and polymer melts, and then this will be the last thing for the exam. So you have an idea of what's happening with viscosity, right? So it's the resistance to flow, and all Newtonian fluids have a defined viscosity. And so I know the chemical engineers will really like this. And so if you make a measurement of the viscosity of a fluid, you build up the shear stress and you have a shear rate that's defined by the gradient of the velocity and the distance. So this shear rate is important because we just talked about time being important. And what's the relationship of rate and time? Rate is just what's that? Yeah, something per time. So higher shear rates mean what? A higher rate is really effectively higher time or lower time? Lower time. So as I increase the shear rate, I'm moving to lower time on this plot. So if I increase the shear rate of a polymer, it's going to be more glassy. And so in effect, this time is usually expressed as a shear rate or as a frequency. And so that's something to watch out for. All right. So shear rate is important because this is time embedded variable. All right. So a Newtonian fluid is defined as a linear relationship between the shear stress and the shear rate, and the slope is a viscosity. This should look familiar, just like elastic solids, right? Elastic solids have a linear relationship between stress and strain. This is not the same as stress and strain, but this is a definition of what a Newtonian fluid is. All right, and you get the viscosity from that. Anything that is not an exact line between shear stress and shear rate, so that's not a line, that's not a line, is a non-Newtonian fluid. And there's lots of cool behaviors of non-Newtonian fluids, but in essence, we have shear thickening fluids. So you see that the stress goes up. As shear rate increases. So the derivative of this curve is higher here than here. So the dynamic viscosity is increasing as we shear it more. The material is getting thicker. You know, things with higher viscosity, we say, are thicker as we shear it more. And that's the opposite of shear thinning. You see the derivative here is less than the derivative here. And so the material is getting less viscous as we shear it more. And if you're confused on what shear rate is, just remember this parallel plate experiment. Higher shear rate means you're moving that top plate faster. And so that's a higher shear rate. So you're shearing it faster. And so you just need to remember which curve is shear thickening. Viscosity is going up. Which curve is shear thinning? Viscosity is going down effectively as you shear faster. So it's easy to mess up, but this is something that you definitely want to remember. Yes?
So on the homework, there's a question, what happens with shear rate to polymer? So how do we know if shear thinning or shear thickening would happen?
Well, let's go and read the question, which I think I have somewhere. Ah, there we go. All right, we're on homework number 9, right? Which number?
1B.
1B. Discuss and explain how you would expect the viscosity of a polystyrene melt to vary with molar mass and shear rate. So the question is polystyrene going to be Newtonian? No, polymers are almost always not Newtonian. The other question is it going to shear thicken or is it going to shear thin, right? Because it can only be one of those. And so I'm going to tell you that in general, polymers are shear thinning. Does anyone know why? Does anyone have a guess as to why in general polymers are shear thinning? As you shear the polymer in this parallel plate experiment, the effective viscosity goes down. Does anyone have a guess? Yeah.
Because you're straightening out the chains.
You're straightening out the chains, and then what happens when you straighten out the chains like that? I mean, why does the viscosity go down? It's easier for them to slide past one another when they're a little bit straightened out. And in that act of shearing, you disentangle them a little bit, right? It's not like you just shear it for a second and then you stop. This is steady state shear. So you're shearing it, which means you're disentangling those polymers. They're wanting to assume their equilibrium conformation. So they're disentangling from one another and you keep shearing it. So the viscosity, the effective viscosity goes down. So polymers in general are shear thinning. So you can answer that. Does anyone know a material that in general is shear thickening? And then you have to know the mechanism. Why does it shear thicken?
Like, I was almost like bootleg, but isn't it like some sort of like thing that like hardens and it's like, I forgot what it's called. It's like particles and they compact. Like,
Yeah. So you're getting it. That's right. So shear thickening means it's viscosity is going up as you shear it faster. And so when it happens in a lot of colloids or in a lot of polymers that have lots of particles in it, it happens in ceramics, it happens in powders, that once those particles start bumping into one another, the effective viscosity goes up. So that's a good answer. Yeah. So we're not going to talk too much about shear thickening materials. We just need to know what they are. But particles bumping into one another, you cause more collisions, the effective viscosity goes up. That's a good example. But in general, polymers most always shear thin because of this straightening out the chains phenomenon. Yes.
For shear thickening, like obviously viscosity goes up as the stress goes up. It's like flow, I guess the viscosity is the flow, that could be wrong, but does the flow ever actually like go down as stress goes up? Like, do you ever see that, or is it just slow?
Well, so you in this experiment, you are controlling the flow. So if you run out of energy, or if you can't move the plate fast enough, it will effectively slow down, but then you'll be at a different shear rate. Yeah. So this is, you need to think, okay, what's practical, or, what's the experience versus what is the thought experiment? And the thought experiment is that you have enough energy to move that plate as fast as you want. So you can go up and up and up in shear rate, and this shear thickening is going to go way up, asymptotically, and you can do that. In reality, like in oobleck or in magnetoelectric damper or something like that, those things shear thicken so much they really slow down the shear rate, and then it goes back. Then it gets softer again. Yeah. Good question. Any other questions? All right. I think this is the last clicker question of the day. Which plot shows a shear thinning fluid? So we know that this is shear thinning. We know that this is Newtonian. We know this is shear thickening. Remember this shear stress versus shear rate. And so the question is how to identify that on a viscosity or an effective viscosity or dynamic viscosity plot. Of course, in some cases, it's even a little bit easier if you remember that the derivative is the dynamic viscosity. Of course, this is shear thickening, and C is shear thinning. Of course, B is Newtonian. There we go. And so shear thinning, great, we got back to 45. So shear thinning is really common in polymers because of this stretching out idea of the chains. Yes.
The formula before, that was just for Newtonian.
Yes, that's right. So this is a linear relationship, and so this is for Newtonian. I guess Newtonian has capital N. All right. So there's really interesting things that can happen. And so lots of times we might want to know the zero shear rate viscosity, right? So as we're at or very close to zero shear rate, we would have a high viscosity. And then we can measure the derivative of that. So if we differentiate this thing, we get the apparent viscosity, NA, or the dynamic viscosity, whatever you want to call it. The apparent viscosity then as a function of log shear rate. So again, this is shear thinning. And you see it a bunch of different ways. And as we talked about, shear thinning occurs because you're elongating or you're relaxing those chains. And so you see this effective viscosity go down as you go to higher and higher shear rate. That feels strange because when we think, I'm going to shear this faster, it's going to feel like it's more viscous. That's not true for polymers because we're taking the local derivative right here. So why is shear thinning in polymers useful? Does anyone know why it might be useful? You know, creep's not that useful. Stress relaxation isn't great. That's why polymer parts break as a, you know, at long time if they're not degrading. But why would shear thinning of polymers be helpful? Yes.
When you increase the flow rate, I think it's time to repeat something.
That's right. So if we want to pump polymers around, we can do it with less energy if it's shear thinning. And that's especially true in injection molding, where we're injecting plastic parts into a die, or we're doing some other plastics processing. Shear thinning helps a lot with that because we can inject the polymer and then it crystallizes or cools down and we get some cool part because of that. So it saves a lot of energy, or we can take advantage of shear thinning in that way. All right, so we just talked about that. So we know that the melt viscosity is really dependent on the molecular weight by orders of magnitude. So here is the degree of polymerization, and we see that the viscosity goes way up as a function of the degree of polymerization. And oftentimes, you see these two different regimes. You have low molecular weight and you have high molecular weight. And knowing what we know now, what's the difference between low molecular weight and high molecular weight in terms of entanglements? Which polymers have more entanglements? High molecular weight. And so you see the slope is higher in the high molecular weight region because you have more entanglements. And so the viscosity is going up much more quickly as you increase the molecular weight versus the low molecular weight region, where the viscosity still goes up as you increase molecular weight, but not as much because there are not as many entanglements. And you'll find out in polymer physics class that there's a key molecular weight where you start to have entanglements, and that defines the kink in this plot. Now, okay, so you can read that. That's great. Yeah, and so this idea of elongated chains and entanglements, this is end chain relaxation plus time plus temperature. All of these things plus flexibility. All of these things impact the properties that we've just talked about. And like I said, I'm going to try and ask you very clear scenarios where we don't have complications of crystallinity and other things like that. But you need to think about how the chains are moving and how that impacts whatever scenario we're discussing. Yes?
So the last question I have is about that's some of the mechanics. What we're looking for, the viscosity effect of it.
Well, so there's a lot of different impacts of entanglements, right? So say, okay, if polymers are more entangled, they do X, Y, Z. If polymers are less entangled, they do X, Y, Z. So discuss creep, discuss modular, or discuss stress relaxation, discuss viscosity. So just give me a couple points for each. Yeah. Any other questions or comments? All right, don't forget your homework. Don't forget office hours. Email me if you need to, and I'll see you on Monday.